All right, so we're going to look at the quantum mechanical model of an atom. This is an advancement from the Bohr model. So looking at the Bohr model, there's some pros and cons. Good things about it is it showed that electrons can absorb energy and release it, and explains how the atomic emission spectra are created. However, it did not explain why electrons should exist in a fixed circular orbit. So, right, the Bohr model said that the electrons go in a circle around the nucleus. So it didn't explain why that was the case, and there was no explanation of why there could not be an infinite number of orbits. Do you remember how many orbits I said would be the max? 7. Good. So this model doesn't explain why there can only be 7 orbits. So this means we need to learn some wave mathematics. So the de Broglie wave equation. He used the photoelectric effect to support that light can behave like a particle rather than a wave. Scientists began to wonder if matter that usually acts like a particle. So an example of something that acts like a particle would be an electron. Could something that normally acts like a particle, could it sometimes act like a wave? So in the late 1800s to the 1900s, this French guy, he created this de Broglie equation that says wavelength equals that constant h over mass times velocity. Your book used that fancy little v thing to kind of show frequency. So with this formula, make sure that you're noting it's not the frequency. And then the other kind of sticking point is the mass must be in kilograms. So let's practice using this equation. It says an electron with a mass of 9.11 times 10 to the negative 31st kilograms is moving at nearly the speed of light. Using a velocity of 3 times 10 to the 8th meters per second, calculate the wavelength of this electron. So all we have to do is use this formula where it says wavelength equals h, the constant, Planck's constant, over mass times velocity. So Planck's constant, 6.626 times 10 to the negative 34th, over your mass, which is given to you in the problem, 9.11 times 10 to the negative 31st, times the velocity, which is again given to you, 3 times 10 to the 8th. And then you calculate that out, and you will get the wavelength of 2.42 times 10 to the negative 12th meters. All right, an electron confined to a particular orbit can only move so that the wave-like path, I'm still on the blue, of the electron fits into that orbit. So what that means is we have to have the crest and trough going, and it has to move so that it fits in the orbit. This is what it's called in phase. If the electron is out of phase, you will see the path of the electron, the start and end point will not be the same. So this demonstrates if the electron is in phase, it demonstrates that the frequencies of electrons are quantized. So that means that the amount of energy required to get the electron in phase is a set amount. If that amount varies at all, we'll get the electron to be out of phase. Using Planck's equation, scientists demonstrated that electrons can only exist at specific energies. This was great because that supported Bohr's idea of different energy levels, of the different orbits. All right, so this brings up, anytime we have something moving in science, it's referred to as mechanics. So mechanics simply means that something is moving. So classical mechanics is studying large objects, things you can see pretty easily with the use of a compound microscope or even just your eyes. Because the size and the mass of these objects are so large, it cannot be affected by quanta of energy. And so objects with classical mechanics do not demonstrate the wave-particle duality. That means they have to be either behaving like a wave or a particle. They don't get to pick which one works. Quantum mechanics then will study particles the size of atoms or smaller. The small quanta of energy can greatly affect the objects of study. So since the objects are so absolutely tiny, it doesn't take a lot of energy to affect the location, the speed, whatnot of that object. This allows these objects to demonstrate the wave-particle duality. So the vocab word here is quantum mechanics. This is the study of the motion of objects that are atomic or subatomic. Subatomic meaning smaller than the atom in size, and thus demonstrate wave-particle duality. All right, that brings us to the Heisenberg uncertainty principle. Heisenberg, not the meth guy from Breaking Bad, says it is impossible. It is impossible to determine simultaneously both the position and velocity of a particle. So in order to detect an electron, photons of light must interact with the electron. However, any interactions of electrons and photons cause the path of the electron to change because both electrons and photons have the same energies. Think of it kind of like pool balls hitting one another. So as the photon hits the electron, this was the original path. It causes the photon to scatter and then the path of the electron to change. So the quantum mechanic model is based off the work of Erwin Schrödinger. He's from Austria in 1926. He developed an insanely complex math equation that accurately describes the behavior in a hydrogen atom. Why would he work with a hydrogen atom? What's the logic there? There's only one electron, so it's simple. He used the idea that these electrons behave with the wave-particle duality. Or duality. The quantum mechanic model is then an atomic model that comes from Schrödinger. The solutions to this equation are called wave functions. And it gives the probability of finding an electron at a given point. This allowed him to conclude that electrons do not travel in perfect circular orbits. We'll just write circular. Instead, he refers to the locations of the electrons as an electron cloud. So this idea is now incorrect. This works to kind of think about it in a two-dimensional sense, But atoms exist as 3 dimensions. And so that's what this model takes into account, is that 3rd dimension. So the electron clouds have variable densities. In a high density electron cloud, there is a high likelihood of electrons being in that area. So then, if it's a low density electron cloud, what would you think the probability of finding electrons there are? The low. So if it's low density, you have a low likelihood of electrons being in that area. So instead of calling the location of electrons orbits, they now say orbital, which refers to a 3-dimensional region of space in which there is a high probability of finding an electron. So as you look at this diagram, the most likely place to find an electron is closer to the nucleus, question mark, or farther away from the nucleus? Closer. Good. Was that Caitlin? Yeah, nice work. Thank you. So because we can see that with the coloration, the darker it is, indicating a high density, the lighter coloration further away from the nucleus, indicating a low density. It is entirely possible. Let me rephrase. You need to think about atoms having no definitive outer edge. An electron can be relatively very far away from the nucleus. There is just a very low possibility of it. Doesn't mean it's impossible, it's just a low possibility. So the farther an electron is away from the nucleus, the more loosely it is held to that atom. That means those outer electrons have a greater ability to jump ship and go to a different molecule or ion or atom. Questions? Nada? All right.